Hello everybody, welcome back to my channel Deep Intelligence Lab. Today we'll be discussing the concept of PCA or Principal Component Analysis, which is one of the most important dimensionality reduction techniques in machine learning. So let's get started. What is PCA? PCA basically finds the directions in which the data varies the most. It uses those directions to represent the data with fewer dimensions while losing minimal dimensions. What is the motivation for PCA? Well, let us discuss about the curse of dimensionality. So whenever the dimensions of data increase, data becomes sparse and the distance becomes less meaningful, and models need to have more data to be able to generalize. Now let us consider a data set x equals x1, x2, so on xn. Here xi's are vectors of dimension d. We can rewrite this data set in matrix format as shown. Here, each row represents one sample data point. So the matrix has the dimension n cross d. The reason we use xi transpose here is to convert each column vector into a row vector format. In this representation, n stands for the number of samples and d stands for the number of features. So now let us move into the concept of PCA. Our first step would be centering the data. Because PCA always assumes that the data has zero mean. First we find the mean vector mu, which is basically the mean of all the data sample vectors. This is written as mu equals 1 by n summation of xi from I equals 1 to n. The data can be centered by subtracting the mu vector from each xi vector. This is represented as xi bar equals xi minus mu. If we had to put the same in matrix format, it would be x bar equals x minus 1 into mu transpose. Here 1 is nothing but a vector of all ones. So 1 into mu transpose becomes a matrix and we end up subtracting the vector mu from all the row vectors of x. So now the mean of the modified data would be 1 by n summation of xi bar from I equals 1 to n, which is nothing but 0 because we have centered the data based on the mean. Now let us talk about a concept called projection. Projection means we ask the question, how much of one vector lies along another vector? Supposing the direction vector is w, the projection of a data point xi on w would be zi equals w transpose xi. If you recollect, in PCA we want to project data onto a lower dimension. Suppose we project the data onto vector w. So we want to find the direction w along which the variance is maximum. So the projection of any data point xi bar can be represented as zi equals w transpose xi bar. Note that xi bar here is the mean centered vector. Here zi is nothing but the coordinate of xi bar along w. W is nothing but a direction vector with dimension d. I reiterate that PCA chooses the direction w such that the variance of projected data is maximized. Now let us define variance mathematically. Variance measures the deviation of data from the mean. It captures how the data varies. So the variance in a data set X can be written as 1 by n summation of xi minus x bar transpose into xi minus x bar from I equals 1 to n. Here xi is a single data point and x bar is the mean of all data points in the dataset. This can be rewritten as 1 by n summation of the norm of xi minus x bar whole square. Now you might ask me why we have this square. The square ensures that positives and negatives do not cancel. Also, it helps farther points have more weightage. Now, assuming we use a mean-centered dataset x bar, the variance of x bar would be written as 1 by n times the summation of xi bar transpose xi bar from I equals 1 to n. This can be rewritten as 1 by n times summation of the norm of xi bar whole square. Now that we have seen the concept of variance, let us move on with PCA. We find the variance of the projected data z. The variance of z is written as 1 by n times the summation of zi square. Here zi is a scalar value. If we replace the value of zi with W transpose xi bar, we get 1 by n times the summation of W transpose xi bar whole square. This captures the variance of xi bar along W. Let us expand this further. We get 1 by n times summation of W transpose xi bar whole transpose into W transpose xi bar. This is nothing but 1 by n times summation of xi bar transpose W transpose xi bar. Here we have used the matrix property of AB whole transpose equals B transpose into A transpose. Here we note that W transpose xi bar and xi bar transpose W are scalar values. Hence we can reshuffle these values as 1 by n summation of W transpose xi bar into xi transpose W. We can separate out W transpose and W from the summation as these do not depend upon I. We get W transpose into 1 by n times summation of xi bar transpose into W. Let us keep this aside for now. What is the concept of covariance? Covariance measures how two variables change together. If we have two variables x and y, the covariance of those would be 1 by n summation of xi minus mu x into yi minus mu y. Here mu x is the mean of all values in the dataset x and mu y is the mean of all values in dataset y. If x and y have positive covariance, it means both increase together. If x and y have negative covariance, it means while one increases, the other decreases. And if x and y have zero covariance, it means both are unrelated. Now covariance in the matrix format would be 1 by n times summation of xi bar into xi bar transpose. Here xi bar is the mean-centered data point. Let us take an example and expand this. Suppose xi bar equals the column matrix containing xi minus mu x and yi minus mu y, then xi bar into xi bar transpose can be expanded as shown. The covariance matrix can now be rewritten. We finally get the matrix with the elements variance of x, covariance of x, y, covariance of y, x and variance of y. This is nothing but a symmetric matrix. That is because covariance of x, y equals covariance of y, x. Now if you remember from earlier, we had the variance of z to be W transpose into 1 by n summation of xi bar transpose into W. Now the middle term can be written as the covariance matrix itself. So we get the variance of z equal to be W transpose sigma into W. Note that most commonly the covariance matrix is represented by sigma. Now we reframe the idea of PCA into an optimization problem. If you remember, we wanted to find the value of W that maximizes the variance. This can be formatted as the optimization problem argmax W of W transpose sigma W, which is nothing but the variance of Z. But here, if we do not have a constraint upon W, it could become arbitrarily large. Hence, we enforce the constraint norm of W square equals 1. So, the final optimization can be written as argmax W of W transpose sigma W subject to W transpose W equals 1. So what we want to solve right now is a constrained optimization problem. And for solving this, we use the method of Lagrangian. Let us look into that. Now let us assume that we have the optimization problem max of f of x and the constraint g of x equals 0. Here, f of x is called the objective function and g of x is called the constraint function. So the core idea behind Lagrangian is that the objective gradient and constraint gradient must point in the same direction. This can be written mathematically as the gradient of f equals lambda into the gradient of g. Here, lambda is called the Lagrange multiplier. It is nothing but a scaling constant. This whole concept can be rewritten as L of x comma lambda equals f of x minus lambda g of x. This is the equation of the Lagrangian, which we try to optimize normally as we would any other optimization problem. So we take the derivatives with respect to x and lambda and equate them to 0. Moving back to PCA, we can rewrite the optimization problem to be L of W comma lambda equals W transpose sigma W minus lambda into W transpose W minus 1. Here we note that G of W should be equal to 0. Hence we have to bring the 1 to the LHS and write G of W as W transpose W minus 1. We now take the gradient with respect to W, which is 2 sigma W minus 2 lambda W and equate it to 0. This gives us sigma W equals lambda W. Do you recognize this equation? Well, it is nothing but the eigenvector equation. Here lambda is the eigenvalue of sigma and W is the eigenvector of sigma. From earlier, we had variance of Z equals W transpose sigma W. This can also be written as W transpose lambda W because we got the relation sigma W equals lambda W. Now lambda being a scalar value, we can separate it out and write variance of Z equals lambda into W transpose W. But if you recollect from the constraint earlier, W transpose W should be equal to 1. Therefore, the variance of Z equals lambda itself. Here the variance along the direction W is equal to lambda. We note that W and lambda here are the eigenvector and eigenvalue of sigma respectively. So for finding the first principal component, we want to maximize the variance, which means we want to find the eigenvector W1 which has the largest eigenvalue lambda 1. So the direction along which the variance is maximum is W1, which is the eigenvector with the largest eigenvalue. And the largest eigenvalue is simply the maximum of lambda, which is the collection of all eigenvalues of sigma. This means that W1 equals argmax norm of W equals 1 W transpose lambda W. If we want to find the second principal component, we need to maximize the remaining variance, but we need to do this without duplicating what W1 already captured. So to avoid getting W2 equals W1, we enforce orthogonality between the two vectors, which implies our constraint would be W2 transpose W1 equals 0. So the optimization problem becomes argmax W of W transpose sigma W subject to W transpose W equals 1 and W transpose W1 equals 0. Now let us see the general PCA solution. We have the covariance matrix sigma from earlier. We use eigenvalue decomposition and decompose it to be V capital lambda V transpose. Here V is a matrix containing eigenvectors as its columns and capital lambda is a diagonal eigenvalue matrix. As we have the whole set of eigenvalues, we sort them in descending order and select the eigenvectors corresponding to the top k eigenvalues. Thus we obtain Wk, which is the matrix of the columns W1, W2, so on Wk. Now, if you remember, our goal is to project the data into a lower dimension. So we obtain Z equals x bar into Wk, where x bar is the mean centered data. Here Z is a matrix of dimensions n cross k. Each row is the low dimensional representation. Now let us see the reconstruction of the original data. We get x cap equals Z into Wk transpose plus 1 into mu transpose. Here mu is the mean vector. This can be rewritten as x bar into Wk transpose plus 1 into mu transpose. Now let us look into something called the variance capture ratio. Often when we want to find the optimal value of k for a particular data set, we use the cumulative explained variance, which is nothing but summation of lambda I from I equals 1 to k divided by summation of lambda j from j equals 1 to d. Here we are trying to find the explained variance when we have k components in the lower dimensional data. We can set a threshold for this value, say 95% or 98%, depending upon our problem statement. Hope you guys enjoyed that. In our next video, we'll be talking about logistic regression. Until then, stay tuned and don't forget to subscribe and hit the bell icon. Thank you.